Hello. Hello.
Yes, sir, you're audible. Yes, sir.
Yes. Okay. So before I start today, any questions, doubts, remarks, anything about whatever has been going on? So did you guys attend the tutorial? Okay. Did you check your copies? Hello. None of you have checked your copies?
Yes, sir. Everyone has.
Everyone has? Okay. Okay, so if you don't have any doubts, that's excellent. So then let me start sharing my screen and
Sir,
yeah.
will we cover backtracking paradigm in this course?
I mean, what do you mean by backtracking paradigm?
The general algorithm paradigm backtracking, where basically we check up to a solution, then go back.
Backtracking paradigm is actually a algorithmic technique for finding for finding solutions in a in something like a CNF or some other solutions. Okay, so now let me tell you this thing, this backtracking paradigm. We will be doing a little bit of that later on, but an important thing is that, see, none of these backtracking paradigms are very good in the worst case. Okay, so whatever we have done till now, almost all the problems that we have done till now has a polynomial time solution. Okay, and for this set of problems, usually backtracking is not useful. Now, there are problems which we will soon see, for which we don't expect to have polynomial time algorithms. So in those problems, various heuristic techniques are applied, and the backtracking is a very powerful tool in those ways. So I don't think I will be covering backtracking paradigm as such, but I will be at least talking about some of the aspects of that thing. Just maybe sometime next week only, I think I will start with this set of problems.
I see, sir. So not like the 8 queens problem and things like that will not be covered.
No, those are not something. No, that will not.
I
be
see.
covered. Yeah.
Because there are no other solutions, so it's very unique in that sense.
Right, but yeah, no,
Okay,
I don't think
understood.
I'll be covering those things.
Understood.
Yeah, so the backtracking solution, except for the toy problems and all, the biggest usage is in the world of what is called as SAT solvers. So if you guys are familiar with it, very good. If you're not familiar with it, don't worry, I will do it in some time. But there is this problem called SAT, or satisfiability, whatever you want to call it, CNF form, and that's a very important problem. Why important? Because again, I'm throwing words which I have not explained in the course till now, so don't be surprised if you don't know it, but that's okay. So the SAT is a NP complete problem, which means that the set of all problems that are on NP can be reduced to SAT. So there are many such problems. SAT is one of them, and SAT is used a lot in understanding a lot of problems. But SAT, we don't expect SAT to have a polynomial time algorithm. So coming up with heuristic algorithms for SAT is a big thing, and we know some very good algorithms for SAT also, heuristic algorithms. So they are algorithms that are not good in worst case runtime, but they're surprisingly good in most for many applications. And for one of the biggest tool of handling SAT is the backtracking algorithms. So yeah. So any other questions? Let me ask you something. There are some 16 or 17 of you are here. Can you guys quickly tell me whether you guys have heard of NP completeness on, or how much do you, is it possible maybe one by one to kind of have a discussion on this? So maybe let me start with the Amit Bhaumik. I mean, this is the first time I'm hearing this name. So Amit Bhaumik, are you there?
Yes. Yes.
So you are in CS or CRS?
Yes.
CRS. Have you heard of NP completeness, NP problems? Hello?
Yes, sir. Yes.
I mean, at least say the yes sir properly. So you know. So can you name one NP complete problem or something?
It's a Hamiltonian graph problem.
Okay. Excellent. So you have been introduced to that. Okay, good. Maybe let's see. Bishwajit Mondal. Bishwajit Mondal, are you there? Okay, I cannot hear you at least. So maybe if you can just send a message or something. Have you been introduced to NP completeness and reducibility and so on? Okay, so maybe yeah, since many of people are, so how many of you have not heard of? Let's see. In that case, accordingly, I can move fast. How many people, if you have not heard, can you just say in the message that no, I'm not that comfortable with what is NP completeness or something? Don't be shy. Anyway, this is the course, so I'm just trying to understand how fast should I go in this dot area. Can you just send a message or something? Okay, so a no message, I will imply that you guys are like an expert in NP completeness and NP reduction and all. Oh, wonderful. So all of you are ready. Okay. So okay, should we know I have heard it from? Yeah. Okay, so what I realized is that so many of you have heard of it, but may not be comfortable with it, and most of you are comfortable with it. Other than that, that's fine. Okay. Okay, so anyway, so this is something that I will not do today. I will do it later in the course, maybe next week or something. So I get an idea and I will plan it accordingly. So for today's class, what I will do is that I will start with, I will continue with this recursive algorithm that we are talking about, but not necessarily dynamic. So I will be doing two problems. Again, these two problems are something that maybe you guys have heard of it already, but I will still do it. So they will indicate. So you have seen merge sort. You can see my screen, right?
Yes, sir, it's visible.
Yeah. So merge sort and quick sort, these were of course recursive algorithms, or if what we can call it as divide and conquer algorithm. Now also we have this, all these various things of dynamic programming that you saw, they are also recursive algorithms. So this first thing that we will start with is a very simple problem of finding median. So what does it mean by that? So, so what is the median? So I have been given some a1 to an, some numbers, they're all numbers in, say, in the real numbers or something. And our goal is to find the median of a1 to an. Now, what is the median? What is the median? So median is basically if you arrange it in the sorted order. So if we order a1 to an in a sorted order, meaning if you arrange them as an increasing way, so let's say b1 is less than or equal to b2 is less than or equal to, and goes on till bn, then the median of that, so bn over 2, this is the median. So the median is now. I am sure there will be some people who will be contesting me in this, and you are completely right. If you have a problem with this particular definition, because it depends upon n. Okay, so for actually speaking, maybe this is not the right definition to give. So this would be bn plus 1 by 2 if n is odd. And what is even? Now the even thing is not very clear. Sometimes people define it like this: if n is even. Sometimes they define it in the average of this n by 2, n by 2 minus 1 subject, and so on. But irrespective of that, so let's for now, this just to be, not just to ensure that we are in a fine thing, let's say n is odd. So in that case, we have this one. Okay. So any questions about this thing? Excellent.
So, sir, you're saying that regardless of what n parity of n is, you're going to say that median is always n plus floor of n plus 1 by 2.
And let's live with this one. Okay. I mean, let's for now. I mean, whatever we are going to do now, today, it will not matter that much how you are defining it. Okay, so you can, for the sake of this this class, you can think that n is odd, and we are going to find this subject. Is it fine?
Yes, I understood.
Okay. Okay. So in that case, let me ask some of you who can help me in this thing. Shantanu Majhi, are you there?
Yes.
Yes. Can you tell me how can we proceed with this? Can you give me an algorithm for finding the median?
Past given any array, we have to sort them,
You can sort them, and then
and then we know the length of the array. So we just check the middle one.
because the output is middle one. Okay. So the first algorithm that you are suggesting to me is the algorithm 1 is sort A1 to AN and output the n plus 1 by 2th element. Right. So this is one thing that you are telling me. Okay. So let me see. Then Soham Das.
Yes, sir.
Yeah. So you just joined, is it?
Sir.
Yeah. So can you tell me, your friend has told that this is an algorithm that will output the median. Do you agree
Yes,
with that?
Yes, sir. It will have,
Okay. So what is the runtime of this?
it will be n log n.
It would be n log n, right? So runtime is n log n. Okay. Why?
Because to sort this array, we need
So
n log n.
sorting
times,
this array takes n log n.
and finding the median, it will be the order of 1.
So this is say order of 1 if you want to do it in, yeah, if you have a RAM model or something, yeah. The question is that can you do better? Is it possible to do better than this? Tomalika Ghosh? Hello. Okay, you're not there. Who is Samipa? Are you there?
Yes, sir.
Yeah. So you are from CS or CRS background?
Yes.
CRS background. So do you have you encountered this problem earlier, finding median?
No, sir.
No. Okay. So do you think you can do better than n log n?
I guess can be done
Hmm?
in time. I guess it can be done in order in time, but
I
thinking
cannot hear you properly. Can you just?
Hello,
Yeah.
sir. Am I audible now?
Yeah, somewhat.
Hello.
Yeah, yeah.
Yeah. I guess the runtime can be ordered in, but I'm just thinking about how to design that.
Right. I mean, okay, so there is an order n algorithm. Yes, completely right. So what I was looking for is that. So while in the case of the sorting, we know that n log n is the best that you can do, but sorting is a bit more than just finding a median, right? Sorting, you can find anything. If I want you to find out all the possible any kth element, you can output that. So sorting, you're doing way too much more than that, than just finding median, right? So you can expect that while we know that sorting cannot be done anytime better than n log n, but maybe there are some other approaches that will help you to find the median in a much quicker form. Okay. So this idea of finding this algorithm, so and now I'm going to try to present you a order n algorithm, and this is purely based on divide and conquer algorithm. Okay. But because of that, I will say I will not do this median. I will say the find element. I have been given this A1 to AN, so this A, this series A, right? So this is the array you can think of. A1 to AN, and I am going to find out the kth element. So the goal will be of this algorithm is input will be A1 to AN in an array A, and the output, that is the kth element in this sorted order of A. So is this clear? So what's going on? So I am going to solve a much more general problem, not just the median, but give me any set of numbers A1 to AN, and there is a sorting, right? Once you sort it, I will output the kth element, a particular k that is also giving as an input. And this is what my job is. So clearly finding median is nothing but given A comma n plus 1 by 2 kind of stuff. Okay. Hello.
Yes,
Yes,
sir.
Yeah. Yeah. So if it is clear, then can you first tell me what is just the, can you find the element A comma 1? What is it?
Minimum.
The minimum element.
Order n time minimum. Yeah.
This is an order n time algorithm, is there, right? Okay. What is find element A comma n?
Maximum, same thing.
It will be the same thing, right? This is also order of n. Okay, good. So they are like kind of checks. Okay. Now, say I want to find the kth element. What happens if I first split up the A into two chunks, the first half and second half? This is not ordered, okay? Say this is the A1 to n by 2, and this is n by 2 plus 1 to AN. So this is first part of A and the second part of A. Okay. So I want to say find the kth element. Correct? So I have found the say kth element over here. I find, oh, see, this is the kth element. So I find element A1 comma K, find element A2 comma K. Okay. So what does it mean? That if I sort this A1 to AN in a particular order, so let me just define this thing to be, say, in the sorted one, the A1 forms B1 is less than or equal to B2 is less than or equal to till Bn over 2, and the A2 is C1 is less than or equal to C2 is less than or equal to Cn over 2, and I know what is Bk is and I know what Ck is. What can I do with these objects? From this thing, can I progress? Can I progress? Can I compute the kth element of the A1 union A2 combined by looking at the kth element of A1 and kth element of A2? What can I say?
Sir, how is A1 and A2 sorted?
No, A1 and A2 are not sorted. Just the first half of A1 A is A1, second half of A2 is A2. So I'm not saying that. Yeah.
No,
Go ahead, Joseph.
So we can, so answering your question, and like I have a doubt that we can at most claim that the kth element would be less than both of Vk and Ck, but I can think of anything more that we can claim from here.
Okay. So let's say I can look at Bk and Ck, right? What happens
Yes.
say without loss of generality? Let's say I find out Bk is less than Ck. What can I say? What does it mean by that? So maybe I should just write it here. So there are this B1 to Bk.
Now we don't have to look at CK and the other part, right? Because we want the
And which
kth.
part? Ck and
So
which part?
CK to the CK plus 1, because the kth largest number would be in A1 or C1 to CK, right?
Right. That's a very good point, right? So that means if Bk is less than or equal to Ck, then I look at this part, okay? Can the kth largest element be part of this set? Then the kth largest element or find element, or no, sorry, maybe I should not write this one. Then the kth element in A. Now I think A meaning this is of course A1 union A2 must be the kth element of which one? It can it be part of any of these elements?
No, sir.
It cannot be part of these elements because it must be in the first k elements, right? So here these are the first k elements. Correct? Here also it can be the first k elements. So it must be part of B1 to Bk and C1 to Ck. That's it. The kth element cannot be any of these or any of this. Right? So that means all I need to do is that, okay, after I find this kth element over here, I can just say that, okay, now find element. So maybe let's call this one to be D, this set D comma K. So in some sense, if I apply these three things, if I apply A1K, then A2K, and then DK, I should be able to done. I should be able to figure it out. Hello.
Yes, sir.
Yes, sir.
Correct. So now the important thing is that the size of A1 is just half of A2, size of A2 is half of A, and maybe size of D is also smaller than A. And this will help us to kind of reduce the big problem into smaller problems. Now, of course, will that help? That's a different issue that we have to think about. But you see how we can progress into breaking this big problem into smaller problems. Hello.
Yes, sir.
So now can you do you guys want to just think a little bit for yourself that using this, how can we may progress into finding a better algorithm? Say even for median, say for that matter, or this find element AK, how can we actually write it? I'm not giving you the whole algorithm. The algorithm is far from being done. I just wanted to show you that by analyzing or by studying it carefully, you can see that breaking it up into smaller parts, or basically applying this find element on smaller set of things, that can be useful.
So one question.
Yeah.
This find element D that we are constructing at the end,
Yes.
essentially for a median, it should be an in-length array itself, right?
Yeah. Good. Very good point. If k equals to n by 2, then that is not making any help, right? If k equals to n by 2, then we are going to have this 2 and we cannot do much. In that case, the d has not gone down that much, right? Okay.
It would always go down by at least one.
It will go down by at least 1, that is true, but that is not very good,
I see.
right? Because you have to go down by a constant factor. To go down by a 1, then that means every time you are spending, you think about it, it's like t of n equals to t of n minus 1 plus order n kind of stuff will come, right?
So instead
So-
of dividing it into 2 equal parts, why not do
3 equal parts.
yeah?
Yeah, think exactly. Good. I want you guys to think. Okay, you guys are doing well. Just think. You're in the right direction.
What was the last thing about 3 equal parts? I just
So
missed it.
instead of A1 and A2, why not I do A1, A2, A3? Now, of course, there will be 3 things that will come up. And then what?
Sir, instead of searching for the kth element, why not k by 2th element?
Yes, you can do that also. And then what happens? We search for the k by 2th element.
Yeah, then we can sort of do this comparison, right?
But then can we really kill this one off? Can I really kill this thing? See this, can I say that this statement?
Yeah, you can't kill everything, but you can kill a part.
You can kill a part. Which part?
So if something is, if the k by 2 element is greater, like bk by 2 is greater than ck by 2, then we can kill the other part, right? Other part of c, like ck plus k by 2 plus 1 things.
Correct. You're completely right. Hello. Yeah. Let me give you guys a few minutes to think, brainstorm, and see what you can do. See, I mean, I'm not expecting you guys to completely get the whole solution, but at least you'll get the hint about what's going on there. Okay. So what you're saying is that what happens if this one, instead of finding it with k, what happens if I do it with say k by 2? So then I have this say bk by 2 here, bk by 2 here. But now question is that what can we talk about it? Our job is to find the kth element, right? And I know the k by 2th element. Okay. So what happens if this is bigger than this? If say bk by 2 is bigger than ck by 2, what can we say? So in other words, where can the kth element lie? Can the kth element be here? Can the kth element be here? Can the kth element be here? So the kth element of A, where can it be? Can it be here? Is it possible that the kth element is here?
No, it is not possible because ck by 2 have already more than k elements before it, right? In the sorted order.
Because there are these k elements, and then there is, since this ck by 2 is bigger than smaller than ck by 2, then this k elements, right?
So k by 2 elements.
K by 2 elements. So k by 2 plus k by 2 is k. So before anything here, there are at least k elements, or there's k elements bigger than smaller than this. So that means it is not possible that the kth largest element is any one of them. Is this clear, this concept to rest of you guys? Amit Bhaumik, are you there? Amit Bhaumik? Arnav, are you
Yes,
there?
sir. Yes, sir. Yes, sir.
Did you understand what is going on?
Yes, sir.
You understood?
Yes, sir.
So in that same logic, why can't there be, why can't I say that it cannot be here?
For dk to be n by 2.
Yes.
Sir, the element must be in the first k element. So b1 to bk should be.
Began to be k by 2 I'm talking about.
Achha.
Okay. So you clearly were not following it at least. Arnav? Arnav, are you there?
Yes.
Can you tell me why can't I say something similar for here, for this point over here?
Sir, can you repeat again the question? The elements cannot be in the ck by 2 plus 1 dot to c by 2 portion.
Yes. Can you understand that? Did you understand that?
Yes, sir, because the bk by 2 is less or equals to ck by 2. Then the k by 2 elements will be the left hand of bk by 2. And next k by 2 elements will be the left hand of ck by 2. So all the k elements will be the left hand of, must be the left portion of ck by 2, not to the right portion of ck by 2.
Okay. Okay, good. Okay, I'm hoping that you guys have understood it. Okay. So in that case, what can you say? What happens to the size of D? What happens to the size of D? What can we say? Is this statement
Size of t will be n minus k.
n minus k, right? Okay, because it will be not be up to k, but it will be up to n and this 1 to k by 2 kind of stuff like that. So n minus k by 2. So size of D,
Sir,
therefore.
why would this be n minus k by 2? It would be n by 2 plus k by 2, right?
Right, you're right. Completely
Because
right.
essentially we are
Right,
getting
you're right,
one
you're
of
right.
n by 2 and k by 2.
Yes, yes. It would be n by 2 plus k by 2. Right? But k can be at least n, or can be as much as n. Right? In that case, what happens? So this must be size of D, therefore, is certainly less than n by 2 plus. So what is k? If k is n by 2 kind of stuff, then we are fine. So if is so this will make us, so size of D is significantly lower than n if k is less than n by 2 kind of stuff, say. If k is less than n by 2, then size of t is less than 3n by 4 kind of stuff. And then I have got that to obtain this solution, I am putting what will I do, right? I will first do it for n by k by 2. This will be by k by 2, right? And I will do this problem with k, right? So basically, if Tn is the worst case for finding worst case runtime, kth element among n elements, then what do I get? Then T of n is equals to 2 times Tn by 2. This is when I am applying this kind of stuff like that, right? And I have to do this thing, which is plus T. Let me just not do this very carefully. Let me do this one like say n by 2 plus k by 2 kind of stuff like that, right? Where if k is less than n by 2, then we have some improvement, and then there is an order n over there to do all the other calculations and all those things, right? But the problem is that if I could have written, okay, what happens if I could have written this statement? If I could have written T of 3n by 4, if I could have, okay, this is not true. If I could have written this thing, then what would have been n is? Can you say what will be T of n is?
So can you restate your question? I didn't understand your question.
So if I could have, so okay, so let me, so if I have a runtime which is like this, then what would be the actual running time of T of n? What would be, if you solve this particular recurrence, what would be T of n? Okay, whatever. You go and think of it that this will actually not end up helping you completely. Okay, you should understand it from by looking at just these two objects. If T of n equals to 2 T of n by 2 plus order n, right? That is almost like what happens in the case of
N log n time, right? At least one n log n term would occur, right?
one n log n time will come in. But still, we are kind of making some understanding about how this whole breaking up into small problems might help us. Okay, good. So let me then give you the final solution, the actual algorithm. Okay, the main algorithm. So like we kind of broke into two parts, let me take it to the other extreme. So I have this A1 to AN. I will break into, I will club them into size of 5 each. And so this is A1 to A5, then A6 to A10, then A whatever, n minus 5 to AN, right? Or maybe n minus 4 to AN. I have split up into 5 chunks each. This is the other extreme form. I want to find what I want to find element A comma K. I want to find the kth element, and I have no idea what K is. Now I should say here, like maybe this is something I should have told you here. The problem here was that this such a kind of a thing, this size of D will go down only if you are guaranteed that K is less than n by 2. Now this is true in the first place, but if in the earlier case, that's what I was doing, the size of D was going down, but K was kind of going remain same, right? That there will be cases when K will be as high as n, and in that case, what do we do? So we want to solve it for any K. I'm not going to assume anything like whether K is less than n by 2 or K is a constant or something. No, nothing.
Sir,
Yeah.
sir, yeah, so if K is say close to n, we can formulate that as a n
Max
minus
case.
k. Yeah,
You can do that.
then
You can do that.
that
There
is-
is a way of doing it. Okay.
yes,
There is a completely other way of doing it, and in that case, you can write a statement somewhat like this. Okay, you can define the runtime somewhat like this. Okay,
okay.
if you do that. But that also is not going to solve you immediately. Okay, because of these two terms, it will give you an n log n kind of stuff. So,
Yes, yes.
so to handle that, we're going to the other extreme. We're going to say that, okay, I have these 5 objects. Okay, now what do? You find the median. Now here I really mean the median in each of the blocks. So here I have a median, I have a median, here I have a median. I compute the median for each of them. Now, how many blocks are there? Number of blocks is, yes, number of blocks is n by 5, right? And to find median in each of them, I will take constant number of things. So there are only 5 objects, literally 5, right? So the find median, this whole thing will take you order n by 5 amount of steps, or in fact order n kind of stuff, like basically, right? So order n number of steps is required to find the median of each of the blocks, right? In fact, I don't have a lot of median, so I would say that I would do a bit more. I would say that sort each of the blocks. I will sort each of the blocks completely. Now, what the same thing, because there are only 5 of them. So how does it matter? It's still constant, right? So number of blocks is n by 5. In order n steps, I can sort each of the blocks. So let's say that I have these blocks. Okay, I have this sorting. So there are, say, B1 is less than B2, is less than B3, is less than B4, is less than B5. Then there is B6, B7, B10, and like that it goes on, right? So this Bn minus 4, Bn minus 3, Bn minus 2, Bn minus 1, and Bn. Now note that I don't know how they are related. Do I have any idea how these two are related? I don't have no idea. Is B1 less than B6? Who knows? Maybe not. Maybe yes. But I know that within each column, they are related. Fine. Good.
So you're picking some index say n by 5, then comparing all elements to n by 5th element, saying if it is less or more. If it is less, it will go into the first block.
No.
Oh
I'm
no!
just,
If it, how are you? I don't understand what you mean by sorting.
so sort. So each of them, so A1 to A5. Oh, sorry. A1 to A5. There are 5 elements, right? How are
These are the
they?
first elements of each block.
This one is this. After
I see.
sorting, they get this.
Yeah, understood. Understood. Okay.
Okay. First, each block has 5 elements. They are sorted. Clear? So this is B1 to B5 is what all the elements have gone into first element, first block. Right?
Yes, sir. Understood.
Good. Now let's look at the central element of each of these blocks. Central element. Okay. Good. How many elements are there?
N by 5.
There are n by 5. Right? Good. Now, what I do is that I find the median of this set. So let's call this one D. Okay, of D. So the median of this. Okay, so let's call this one this A something like PK is this median. Okay. Fine. And I arrange it in such a way, let's say all of them, all of these elements are less than BK and all of them are more than BK. I have not sorted them.
This is order n operation.
Not ordering, not full ordering. I've just placed it.
No,
I've
no.
pivoted it.
I'm saying it's order n operation.
It's an
What
order
you-
n operation,
Yeah, yeah.
right? It's a pivoted. I pivoted on this thing. Okay, find the median of PK. Let it be BK. Okay. Now consider all the elements of D meaning the central one, that are less than BK and all of them that are more than BK. Okay, so things that are left, I'm not saying that these are fully ordered, but I know that this set, this contains all of them that are less than BK and all of them are more than BK. Okay. Okay, now good. Now see, everyone with me? You understand what I have done till now? So how much time does it take? Let's see. Okay, so if T of n is the time taken for this whole thing, I have spent,
Sir,
yeah.
sir, I don't get it properly. Can you please tell me that the third element of each column will be in ordered form?
No, it's not in order form. I have found the median. I found the median. Okay, so median is this one. Okay,
Okay.
and I have kind of pivoted it, meaning all the elements of the third elements which are less than BK, I have put it in the left hand side. So these are less than BK and these are more than BK.
Okay, you have changed the ordering of the columns, right?
I have changed the ordering of the columns. Let's say I have
It's
not
not-
done it necessarily, but I mean, at least I know it. I'm writing it in a visual way, right?
Okay.
Okay. So I sorted them, which took me ordered n steps, so sorted each of the smaller blocks. Then I found the median that took T of n by k, n by 5, right? So T of n and this is T of n by 5. And after that, I have kind of considered all the elements that are less than BK and more than BK, and this is taking order n. Okay. Now let's see. I want to find the kth element here. Okay, I will split up into two parts. So say k is n by 2. Then what all things can I say? Note that all the elements over here, okay, maybe I can use a color, okay, like a green color, okay. All the elements in, okay, so let me, all the elements in this green color, they are all less than bk, right?
Yes.
All the elements here, these two elements are less than bk,
Yes.
and all of them are also less than bk, because they are less than b3. This is less than b5 bk, right? So this whole element is less than bk.
Yes, sir.
Yes,
Right?
sir.
Good. Now let's do the other direction. All of all of them are more than bk. All of these are more than bk, and all of these are also more than bk. Right?
Yes,
So how
sir.
many elements are more than bk and how many elements are less than bk? Certainly, we can say.
N by 4 elements are less than bk and n by 4 elements are more than.
So that means n by 4 elements, actually you have to do a bit more clever calculation. It's not n by 4 or something. Let's see. Okay, so this is 3 by 5 into n by 2 is the element that are more than bk, right? And 3 by 5 means, you can see there are 3 of them, right?
Yes, sir.
Into
Yes,
n by 2 is more than bk. Okay, good. So I want to find the,
Minus one, I guess.
oh, this k was a very bad shit thing. So maybe I should write, forget. I don't want to find the k. I want to find this is L. Okay. No, sorry. Yeah, n by 2 minus 1, right? That's what you're saying, right?
3 by 5 into n by 2 minus 1 because we are here.
Yeah, minus 1. Yeah. So let's.
K also.
Yeah, I mean, you can do the calculation exactly. It's actually slightly more than minus 1 also, because
Plus 2 by 5 would be
plus
there.
2 by 5. But anyways, in terms of order notation, it's just some small constants here and there off, right? Some additive constants, right? So they're like, so this one is, this should be n minus 1 by 2 plus 2 or something. That's what will be the actual number. And similarly here.
Yes, yes.
Okay, so that's, yeah. Okay, so now if I want to find the Lth object, what do I do?
If the collective size of the green block
Yeah,
is L, then bk is guaranteed to be the Lth element, right?
then bk is not guaranteed to be if sorry, if no, see these things, what we are not sure is how are these elements be related to bk. I cannot say that this bk is this element. I know this from bk, these are all these elements are small. Some of these elements might be also smaller than bk.
So if L is larger than K, we can eliminate the green colored elements, and if L is smaller than K, we can eliminate the blue colored elements.
Exactly. If L is bigger than this quantity, right?
Yes,
L is
yes.
bigger than what? L is bigger than this element. Okay. So if L is bigger than this elements, just let me just quickly see what happens. And this, if L is bigger than into n minus 1 by 2 plus 2, then what happens?
So, why can we not just directly like apply the condition on K? If L is greater than K, we can eliminate the entire green colored element, right?
No, what is K?
Because,
This one?
yes, the K.
Okay,
so-
maybe you're right. Yes, right. So if L is bigger than K, right? Yes. If L is bigger than K, then yeah, yes. So then I know that this might, so then BK is less than
Sir, I'm sorry, but actually, okay, yes, K would be there. No, I was confused. I was thinking that K is an identifier for the 5 groups. So it's not, it's the identifier of the element. So it would be directly K.
yes. So K is basically not K. So K, we know what K is, right? What is K? So K is basically the 3n by K is this object, right? So there are n by 5 elements, so n by 10. Right?
3n by 10.
Why is 3n by 10?
So there are 3.
K is almost n by 2, right?
What is K? What is 3? Oh, right. Forget it. Yeah.
K is almost approximately n by 2.
Yeah. No, I made a mistake. Yeah, you are completely right. So I had to do one more check actually. So see, this is the okay. So there was a confusion with this K. What is BK? Okay. So the BK was this. What was this BK? BK is the median of these objects, right? BK is the median of this D objects. Maybe I should. So this objects BK is the median. Okay, good. So this is the, I don't have to necessarily define as BK. Maybe I can define it as something else. Maybe let's define it as B. Okay, so B is the median of this set of objects. And now I have, first of all, I have done this one is that I found all of these objects that are less than B, all of these objects that are less than B, and all of these objects that are more than B. And this was what I have done for my understanding. And then I have realized that all of these green objects are certainly less than B, right? And all of these blue objects are certainly less than B, more than B. Good. So that means there are at least this many number of elements that are more than less than B, and at least this many number of elements that are more than B. So then what I do is that I take this B and partition this A, the whole set, into A1 and A2. So how? So these are basically, these are the things, the whole A1, these are less than B. Then I have the median. Note that this is not the median of the whole thing. This is the median of this set, only D. Okay. So B is the median of D. So B is the median of D. So I cannot say that it is exactly half and half. So maybe it might very well be very skewed. If I'm splitting up A1, this A into these two parts, less than B and more than B, B is not necessarily the median of the whole set. But what I'm guaranteed that all the green elements are certainly less than B. That means the size of this A1 is more than or equal to the size of the green set, which is 3 by 5 say into n minus 1 by 2 minus plus 2 or something. And similarly, size of A2 is more than this plus 2, right? So while I have not found the median, but I have managed to find a pivot which is sitting somewhere in the middle, meaning it is not completely to the left, not completely to the right. So this chunk is basically has something like 3n over 3 by 10 elements over here, and this also has at least 3 by n 10 elements over here. Okay. So now what do I do? Now it's kind of simple, right? Let me change the color. That if, so I am looking at, I have done all of these things and I want to do find element what? A comma L. Now, simple thing, right? If A1, size of A1 is less than L, what do I know? That means the element that I'm looking at must be over here. Then I would say that, okay, in that case, find element what? Say BA2 means B and A2 combined, comma L minus size of A1. See, I was looking at the 100th element. So say size of A1 is, say size of A1 is 20, and I'm looking at the L equals to 100. I want to look at the 100th element. So then what should I do? I should look at the 80th element in this set, right? Because I know everything else is less than this. And on the other hand, if size of A1 is more than L, meaning I'm looking, size of A1 is say 120, then I know that all I have to look at is the 100th element in A1. So in that case, find element A1 comma L, and that is it. So important thing that happened here is that I started with a array of size n, and I'm going to do, I have done some work. How much work have I done? I have done work of order of n, and there is a t of n by 5. Okay, I will come to that. But then I'm applying this find element on two stuffs, either this or this, not both. And in both of them, how big is this? They are not more than, I've removed at least n by 10 elements. So they are less than 9 by 10. So is this algorithm clear?
So you have removed 3 by 10 elements, right?
3 by 10 elements. I've
So
removed
7
3
by 10. 7
Yes.
by 10.
Yes, yes. So size of A2 comma size of A1, both of them are less than 7n by 10. Okay, this is an observation you can think of. So this is the algorithm. The algorithm does that I first split up into small blocks. I will first do all of these non-trivial objects by first sorting them, and inside this
So,
look at the
sir,
central third element of all of them, find a median. So that is the B. Okay. Now, once we find the B, I would look at all these things that are less than B and that are bigger than B. And depending on how big, how many elements are less than B and how many elements are bigger than B, I am going to proceed.
is the following correct? Order n time to initial split and sorting of 5 chunks. Tn by 5 time to find the median of the third row.
Correct. Yes.
Then order n time to arrange them with respect to the pivot, and then T7n by 2 time, 7n by 10 time to do everything else that remains.
Exactly.
Okay. Okay.
So if you want to do the runtime, so to compute the whole thing, I have of course done some order n steps to kind of go and split up into small chunks and all of them. Then, and so this is the time taken to break it up into chunks and order each chunk. Then T of n by 5 to find the median of that. Then again an order n time to kind of split up into these 3 parts, less than B and bigger than B. And then T of 7n by 10 to find out the element of in this setting. So this basically becomes T of n by 5 plus T of 7n by 10 plus order n. Okay. Now, you might be thinking that how does help this one? Actually, if you think of it, this is nothing but 2n by 10 plus T7n by 10 plus order n. So if you add the 7n plus 2n, this is 9n by 10. So it's going down. So if you compute this particular recurrence relation, okay, what you will get is that T of n equals to order n.
So a question, the key difference between splitting in 2 halves and five chunks is that in the 2 half situation, there was a 2 being multiplied to 3 of n by 2, which contributed the 2 to the n log n term,
exactly.
Right?
Exactly. So I have just here I am kind of putting all of these constants within this thing, right? Of finding the small chunks there and all those things. Yes, that's the constant. Yeah. And so only we are applying it on the big chunk. And I'm doing it only once. So is this algorithm clear? Or should I repeat some of it again?
So what's so special about 5?
Not so special about 5. Go and think about it. There's no speciality about 5.
Any odd number would do, right?
Any odd number will do. Okay. Any even number will also do, actually speaking.
But we have
the constant starts changing.
I see.
Okay. So and somehow if you optimize the constants, then you will find out the 5 is basically the best that you can think of.
Sir, for odd, for even number, some confusion will be there to choose the.
Yeah, it's like a bit of confusion, but you have to kind of check the. Say if you have do it in 4 steps, then you take the third step always, third number always. It's not a big thing. It's just that it will be a bit of an uneven thing.
Yes.
It's just a bit uneven. That's all. So it's as such, it doesn't cause any problem. Okay. So is this fine?
Sir, it got a bit confusing at the end, so we have to. I think I have to go through it once before saying
Yes. Yes, this is a bit involved. Okay, I completely agree with it. So you have to go through it very carefully. But the basic idea is again the same, is that you want to split up into small problems, solve it in that small problems, and combine them together. It is not as straightforward as many other algorithms that we have seen till now. Okay, but it is not complicated. So maybe I will of course upload all the slides and the not slides, the notes and the lecture recording online. So please go over it.
Hello, sir.
Yeah, yeah.
So I mentioned it in the chat earlier.
Yeah.
So I earlier studied a randomized algorithm to find median that has an average running time of ON, and like worst case would be ON squared and best case would be O1. It basically like takes a pivot and then
Yes.
takes a smaller and accordingly. So what are the trade-offs, if you can discuss, and then we can have like study our own time.
So when you're talking about
there's a trade-offs and what are the if we are studying both the algorithms, what is the difference of that?
Yeah, so see, what you algorithm that you are talking about, the randomized algorithm, okay. The advantages of deterministic algorithm or randomized algorithm is kind of almost obvious. Why? Basically, in the case of the randomized algorithms, it is an average case thing. There will be certain times it can go up to order n square. Okay.
Yes.
But here it is always order n. Okay, that is one part of it. Okay, that's kind of the most natural thing. Now you can ask you, why would people want to do randomized algorithm compared to deterministic algorithms?
Yes, and also when we are studying randomized, you mentioned that the constant in that case is lower, so hence that is more preferred in some sense. So is that case also true for this?
That is somewhat true for this, but that's not the main problem. So one of the main problem is that this algorithm is quite complicated.
Yes.
Okay. So this algorithm is quite complicated and a lot of bookkeeping has to be done and so on. Simplicity of algorithm is also something very useful many times. Okay.
Yes.
That is why people sometimes go for very simple, but maybe not so good always kind of algorithm. Okay. But yeah, so this algorithm, in terms of practice, unless you kind of, and also this algorithm is somewhat not very parallelizable. Although it is a divide and conquer algorithm, it is not very parallelizable because it's not like say merge sort, where you can give it two machines, two different parts, and say, oh, go and do it, and then I will combine it. This algorithm is very, although it's divide and conquer, it is a very linear order. You cannot, unless you compute B, you don't know how to split up into less than B and bigger than B.
Sir, a question.
Yeah.
Say you remove the green chunk.
Yes.
Now, whatever you're left with, you have to merge those.
I'm not removed green chunk. Okay, good point. I have not removed green chunk. Okay, I am going to remove either less than B or more than B. The green chunk and blue chunk, but just to convince us that the size of A1 and size of A2 must be must be big. Okay, we don't need to compute the green chunk ever.
Oh, I see. It's still in two halves. You still divide the original array in two halves.
Into two halves, less than B and greater than B. Only that I'm talking about is that, maybe if I can draw it here, that the green chunk, you can see I'm drawing a green chunk is a subset of A, and the blue chunk is a subset of A2.
The only difference between the randomized algorithm that Debarshi suggested is that here the pivot you're choosing is very specific.
It's very specific. Yes. Here the pivot that I'm choosing is very specific. Okay, there is another thing that is there. A randomization sometimes can be very useful in the sense that, see here, when we are talking about it, we don't have any randomness, right? So it might be that the algorithm has been given, the data has been so given that I am hitting the extreme cases. Okay. In the worst case scenario, I might be that, oh, that the A1 is just the green chunk only. So that means I am hitting this end. This becomes a tight thing. That A1 is actually 7n by 10. And this is what I'm hitting every time. Okay. So in this analysis, this will be 7n by 10 only. Every time I'm hitting 7n by 10. But in the case of randomization, okay, this chance of it being 7n by 10 is very low. You would be with high chance be typically between so if you run it a few times, you will basically get close to n by 2 over here instead of 7n by 10. So in that sense, on expectation, I think you can prove that the randomized algorithms expected runtime will be better than the runtime of this algorithm. In the
constant terms, right?
In the constant terms.
Yeah.
Yeah. I mean, that is because in the randomized world, the adversary doesn't have any role to play. I mean, who gives what? I don't care. I'm just blindly doing things. But here, since I have a deterministic algorithm, the adversary can give a particular input which will make my algorithm go in the worst possible way. Okay. Okay. Yeah, good. So, any other questions? By the how long is it? I mean, what is the time now in India? It is 1, right?
1.
And how long is the class actually today? Till 1:20 or something? Is it?
Yes, sir. Up to 120.
Up to 1:20, right? Okay, so maybe I will then continue a little bit for another 10 minutes and talk about another problem. But it is a very kind of high level picture. But before I do that, I mean, any other questions about this median problem? Okay, please go back, think about it, and try to understand it. Come back with any questions that you have.
So you said that 5 turns out to be the optimal value for the constants.
Yeah.
Can you suggest a resource on that?
You can, if you just search it in the internet, and you will find out there are lots of work on this thing. Okay. I mean, why is the 5 the best? Why is 3 not good? Why is 7 not good? And all those things are there. Okay. So let me go to another problem. And this is a problem that is a very, very important concept. This is of matrix multiplication. Okay, all of us know what is it. Say I have given A, say an n cross n matrix, and another matrix B, n cross n. I want to compute it into another matrix of size C, n cross n. Now, this is something that you guys have seen it possibly in machine learning and statistics and all. This is like done all over the time. But question is that how much time does it take to compute the product of two matrices? Can you guys guess or tell me? Can you give me an algorithm for it? Let me ask some people. Venkatesh, are you there?
Yes, sir.
Sir, can you just repeat the problem once?
Yeah, the
I
problem
lost
is
the
that you have
connection
been given two. The input is A and B, and you have to output C.
Sir,
Okay,
we
okay,
can-
just matrix multiplication.
we can
Just
reduce
matrix.
this. We can reduce this to the problem of multiplying two vectors, which can be done in order in time. Then take each column of B, multiply it with each row of A. For any given column, you'll have to do n order in operations, so n square time, and there are n columns in B, so n cube time.
N cube times. Okay, there's a multiple ways of seeing this particular problem. Like, what is Cij? What is Cij?
Cij is the
Yeah, go ahead.
ith row of A multiplied with jth column of B.
Right? The jth column of B. So Cij is nothing but ith row dot bj, right? And this is n bit vector. This is the n bit vector, so you can compute it in order n steps. Right? So any of the bits of any element of C can be computed in order n steps. There are n square different points of C. So the all total, so the algorithm 1, this can be done in order n cube. Any doubt about this? Thomas Kanti Kodai? Thomas Kanti Kodai, are you there? Okay. Sankalpa Roy?
Sir, hello.
Yeah, yeah.
Sir, I think my mic is sometimes breaking, so I write something in the chat box.
Okay, okay, okay. Yeah, yeah. Sure, okay. Okay, good. So anyone has any doubt about this particular algorithm? Order n cube? No one, right? I hope. But it turns out this is not the best. You can do much better. Much, much, much better. So people for a long time did not believe how it can be done. So the basic thing is that, okay, why not apply divide and conquer algorithm? So why? How? So I can split up this algorithm, the matrix A, into 4 parts: A1, A2, A3, A4. Similarly, I can write B as 4 parts: B1, B2, B3, B4. And now, if I think of this C to be also breaking up into 4 parts, C1, C2, C3, C4, then what all can I say? I can know the C1 is nothing but, can somebody say?
A2, B3.
Hmm?
A1, B1 plus A2, B3.
Plus A2, B3. A2, B3. What is C2? C2
A1,
is
B2, A2, B4.
A1, B2 plus A2, B4. C. What is C3?
A3, B1, A4, B3.
A4, B3. And C4 is A3, B2 plus B4, A4. A4, B4. Now, thing is that, so that means if I decide, if I say that P of n, this is the time complexity, time to multiply two n cross n matrices, then what can we say? This all of them are multiplying to n by 2 cross n by 2 matrices. Excellent. So this means that, sorry, this is equals to Tn by 2. How many times am I doing it? How many different multiplications am I doing? 1, 2, 3, 4, 5, 6, 7, 8. So I'm doing 8 n by 2 matrices plus order n. Problem is that if you solve it this way, what you realize is that this gives you Tn equals to order n cube again. No gain, nothing, no advantage. So basically, because this is n by 2 becomes n cube by 8, and this 8 will kind of cancel out. So if only this 8 could have been lower than 8, this could have been 7 or something, then that would have been done. Now, this was how it was till one fine day, a gentleman called Strassen came up with an outstanding observation. So the observation is so complicated that I don't know how to write it. Instead, I'm going to show it to you. Where is it gone? Yes. See here. He says that if I split up, you can see my screen, right?
Yes,
Hello?
sir.
If you can write A as this A11, A12, A21, A22, I mean like this A1, A2, A3, A4 that I've done, then while this is the most natural combination of doing it, right? This is, I can see my screen, this cursor. What he told is that, okay, instead of that, why don't I compute this set of 7 objects? M1, M2, M3, M4, M5, M6, M7. And he kind of told that, see, each of them requires only one multiplication. Okay, how did he come up with it is something that we can discuss about it later. But each of them has just only one multiplication and some addition, but additions are not costly, right? Multiplication is the one that's costly. Additions take order n steps. And if you can do this m operations, then this C11, C12, C21, C22 can be written as a addition of these objects. Sorry? Hello? So isn't this kind of a magical thing? If you can go and check it out, that it actually works out. It actually works out. So what does it mean? That to compute C1, this multiplication of A and B, which is on n variable, n cross n matrices, all I had to do is 7 matrix multiplication of order n by 2, which means T of n equals to 7 Tn by 2 plus order n. And if you solve this particular reconciliation, you realize
the log base 2 of 7, right?
yes, log base 2 of 7, which is 2.78 or something.
Sir, isn't this just the Karatsuba integer multiplication trick, but applied to a higher dimension?
Yeah, so this came first and then all of that.
Oh, I see. Okay.
Okay. Now, this really was the major breakthrough in this world of numerical analysis, numerical algorithms. that something that people did not believe can be done in better than order n cube suddenly can be done in order n to the power 2.78. Now, since then, the question came, what is this the best? And all I can say is that in the last 30 years or so, a small industry has come out. And right now, if I'm not wrong, the best matrix multiplication algorithm this is of the order of n to the power 2.39. The algorithm is quite complicated, not as beautiful as Strassen's, but you also have this improvement. There have been some outstanding connections made between matrix multiplication with topics like sunflower lemma, with topics like group theory, various things. This is called the Coppersmith-Winograd algorithm that was recently improved slightly by Virginia. Now, people don't believe this is the best. People believe now that this number can be even pushed further down. So that is why we don't denote it like this. We always denote it as n to the power omega. That omega value changes. What is the omega value? We don't know. So this is n to the power omega, and people believe, this is a belief, it is not yet done, that omega can be 2. So in order n square steps, you should be able to output the product of two matrices. Now you understand that if you can improve this algorithm by even a little bit, that's a groundbreaking work, because that has immediate applications, immediate effect in all the various softwares that you run. I mean, shaving off, this is one of the most used algorithm in the world of multiplying two vectors, particularly with the world of machine learning and all taking over. So much of it is done in that world. And this, I mean, a lot of things can be done. But it's all started with this beautiful observation of Strassen, that you can divide it into smaller parts and magically use the smaller computations to produce the bigger one.
Sir, an associated question, you mentioned NP complete problems. Can we even verify it in an order?
Yes, NP complete problems can be verified. Okay, I will come to that. I'll come to all of that thing.
Okay.
I'll come to all of that.
Sir, two questions.
Yes.
The first is that the ON, again, I am having some connection problem. What is the ON term in that 8 or 7n by 10 plus ON? That is the recombination cost? Or
Yeah,
what?
these are recommendations. See, you have to anyway play with all of these things, right? You have to add them up. You have to put them together. So that's an order n.
So that is an order n. And second thing
Actually,
is that,
sorry. I don't mean order n. I made a mistake there. This is order n square.
Okay, so now that makes sense. Yeah.
Okay.
Okay. And another thing is that when we are like for these kind of algorithms, is there any sort of lower bound or anything?
No, not that we know of. No, that's another big question. That's a very big question. See, lower bounds is always a very hard problem in the world of complexity or algorithms. Okay. I mean, our understanding of lower bounds is very, very, very less.
So you're saying that there is no reason to believe that omega is true. It's just like faith.
No. In fact, people believe that omega is true. That's a different issue.
I see. So I thought people have shown that it can, at like best is possible is omega equal to. We don't have a lower.
No. Below 2 you cannot have, right? How can you have below 2? Because you are anyways outputting a matrix of size n square. Right, you will need n order n square to even write down the
Right,
matrix.
true.
So less than n square is
Yeah.
cannot done. That we know.
Right.
But why can't we do n square? Is there a reason to believe that you cannot improve beyond 2.1? No, nothing like that is known. Nothing like that is known. Yeah.
Okay. And also, like, if we have time to the later on, can we just discuss regarding if we can prove lower bound for some of the problems that we discussed, like MSP and the median one today?
Yeah. So first of all, see the median one, for example, you can obtain a order n. Yeah. So good. So forget the median. Can you prove to me that you need at least order n steps to finding the maximum?
Yes, because we have to eliminate at least n-1 terms, and for that we need at least n-1 comparisons, because each comparison cannot eliminate more than one term over there.
That
so
is not true. One comparison might eliminate more
n
than
by
one term
2.
suddenly. You are kind of building on and all those things, right? I know that A is
Yes.
less than B. I know C is less than B. I mean, I can
Yes.
understand what you are saying. It's an amortized thing.
Yes.
You have to do
Over
it in a bit.
time.
So
Suppose
one-
such an algorithm existed, go to the maximum and replace it by its negative or something. Then the algorithm would find the same index without having dealt with that number.
Right. So good. So that is one way of, so formalizing this kind of lower bounds is always a very tricky thing to do. Okay. So here is one formulation that I kind of like very well of this particular problem. So I have this n objects. So all I'm doing is that finding the maximum, right?
Yes.
I have n objects. If I compare between any two things, I draw an edge. Okay.
Yes.
Now I want it to be connected, right? If these things are not connected, then I can
Minimum number of
make
edges in a
any one of them bigger or higher or smaller by adding some numbers to all of the elements in the same connected component, right?
So, sir, I did not understand the last argument.
Okay, so if I have an algorithm that is not that produces a graph that is not connected. Okay. So I have I have compared these two. This is less than this. I've compared this to this more than this. All of this kind of stuff have come up, right?
Yes.
So in that case, if these are not connected, okay, and you are telling me that you will find out a maximum. If your algorithm is outputting a maximum from this thing, this component, what I will do is that I will add 1000 to each of them.
Yes, and then
then my algorithm will be wrong, right?
Yes.
And vice versa.
Yes.
If the graph is not connected, then I can always make your algorithm go wrong.
Yes.
So that means your graph must be connected.
At least n-1 edges.
So at least n-1 ordered comparisons has to be required.
Yes.
Okay. So if n-1 comparisons is required for finding maximum or minimum, then at least n-1 comparisons are also required for finding median, or in general, the same argument will go through.
Okay. Yeah.
Okay. Now, what about other things, MST and so on and so forth? I have to say, I mean, we will do at some point, we will go back to graph algorithms maybe in next week or something, when we will do shortest path algorithm, something that we have not done. And we will realize that even there, lower bounds are something that really we have very little knowledge of. Okay. So
just another thing as well. So last class we discussed one reduction related example of that LCS, right?
Correct.
So can we do like there is something that is setting up on that has lower bounds calculated based on some reduction technique.
Right.
So, like if we have a separate class or
No, we
anything that
will. This whole concept of NP and NP completeness cannot be done without doing reduction.
Okay.
So the whole concept of those things, NP completeness and all of those things has to go through reduction. So we will spend quite a lot of time on reduction.
Okay.
So reduction is one of the most crucial concept in the whole course on algorithms. So in the next
purpose is the purpose that if you can show that reduced thing is NP complete, then the thing from which it is coming
right.
cannot.
Yeah.
I see.
Yeah. In
Equivalence.
fact, the definition of NP completeness comes from the reduction.
I see.
Okay.
Yeah. So we will be doing all of that. So in the next class, next 2 classes rather, I will be going back to a non-recursive algorithms. To keep you guys motivated, I will start with a greedy algorithm on a machine learning problem, which is called binary classification algorithm. You guys have heard of it possibly, but never seen a full proof of it, I'm certain. It's called the perceptron learning algorithm. And I'm going to do that. Okay, it's a beautiful algorithm, one of my favorite algorithms, which is quite amazing because it's a beautiful algorithm, but proof of that algorithm, proof of correctness of the algorithm is even more shocking to some level. So, and then we will possibly do a little bit detour on other greedy algorithms, namely shortest path algorithms. And then we will move to this reductions, NP completeness and all. So the next week will possibly the last week while we do this kind of toyish algorithms. And then we will talk about more generic big hammers to solve more harder problems. Okay, so we will be going into a little bit of linear programming algorithms, a little bit of SAT based algorithms, and then talking about the classes, complexity classes of P, NP, NP completeness, and so on. So I think there I have after this thing around 10 classes. So you can think of that we will have something like 8 classes or 7 classes on those kind of stuff. Okay. Yeah. So good. So any other questions?
Are we done with divide and conquer? So we will not do FFT.
No, I don't think I have time for FFT. I really don't think I have time for FFT, but I will see if I. Yeah.
Going to network flow, right?
I will go to network flow. Yeah.
Problems.
Yes. I will do network flow, but that I will do more from the LP point of view.
Okay.
Yeah. Okay. Yeah, there's a lot of things that I have to kind of move out from this course, and as you can see, maybe I have kind of slowed down even further than what I was doing in the last before the midterm, because I think that is very important for you guys to participate in this course, participate as much as possible, and again, please, whoever is attending, whoever is interested, try to participate as much in the class, which will help you to get your algorithmic concepts right and do well in your exams. Okay, I think stop here today, and okay, thanks.